Large language models, or LLMs, now read research papers, inspect codebases, and answer questions across thousands of documents. Yet each model can only attend to a fixed amount of text at once, called its context window, and performance often degrades before that window fills. Think of a brilliant research assistant with a small desk. Give them a 10-page report and they excel. Hand them 10,000 pages and they start forgetting the early ones. This lesson explains why long prompts cause quality collapse, why bigger windows and compression fall short, and how recursive language models, or RLMs, treat the prompt as an external object in a code environment. We will trace one concrete failure through the design, the evidence, and the open problems. Start with a concrete task. Suppose you have a log of users with labeled entries, and you need every pair of users where both have at least one entry labeled numeric value or location. With n users, possible pairs grow roughly as n squared. Doubling the log makes the required work 4 times larger. This is quadratic work, unlike finding one fact, which needs constant work regardless of length, or labeling every entry once, which needs linear work. Paste the entire log into a chat model, and it usually fails, outputting a few pairs, inventing labels, or returning nothing. Summarizing early entries destroys exactly the fine-grained labels needed. A bigger window delays the problem, but does not solve it. The task demands considering all combinations, which one forward pass or a few summarization steps cannot do. Before the fix, a few foundations. A context window is the maximum number of tokens, or text pieces, a model can process in one call. Even inside that window, accuracy drops as the prompt grows. Researchers call this context rot. Inference-time scaling means improving quality with extra computation at answer time rather than retraining the weights. A RePL, or read-eval-print loop, is an interactive programming environment where commands execute and print results. Python's interpreter is a familiar example. A symbolic handle is a variable name standing for a large object, so the model can refer to the prompt without reading it all. This is stronger than retrieval-augmented generation, which pastes a few retrieved chunks into the prompt. Here, the entire prompt stays outside the model as a first-class object. Finally, a verbalized subcall is the model announcing a subagent and appending the reply to the chat history, while a programmatic subcall is code that invokes a function and stores the result in a variable, keeping the root history small. The core idea is simple to state. Given a prompt P much longer than the context window, do not place P in the context. Instead, load P into a persistent Python RePL as a variable, often called context. The root model, the main model driving the scaffold, receives only small metadata, the prompt's length, a short peek, and chunk boundaries. It writes Python code that inspects, slices, and transforms context. It can call a submodel on a snippet through a query function, that is a leaf subcall. It can also call a new RLM on a subset of the data, which is recursion. Only truncated output from each executed step returns to the root history. When the code sets a variable named final, that value becomes the answer, and because the answer comes from the environment, it can be arbitrarily long. A typical pattern loops over chunks, has a submodel extract facts from each, stores them in a list, aggregates, and sets final. Why is this more expressive than simpler scaffolds? 3 choices matter. First, a symbolic handle to the prompt instead of pasting P into the chat history. This alone lets the system handle prompts far larger than the window. Second, the final answer comes from environment state instead of a model-generated finish action, so the output is not bounded by the context window. Third, subcalls happen programmatically inside loops, not by narrating every subagent call. One line of code can launch hundreds of subcalls and store their results in variables. Weaker scaffolds fail on dense tasks. Compaction, summarizing old context when it fills, destroys fine-grained detail. A scaffold with only verbalized subcalls fills the root history with every subagent reply. RLMs avoid both traps because the prompt stays external, the answer is a variable, and recursion lives inside code. The paper tests this with tasks whose required work scales differently with length. SNIAH, single needle in a haystack, asks for one fact hidden in noise, so the work is roughly constant. OOLONG is a linear aggregation task. Label every entry and count the labels, so every entry matters. OOLONG, pairs is the quadratic pair listing task from our example. BrowseComp Plus asks multi-hop questions across 1,000 documents, adding retrieval pressure. CodeQA, code question answering, tests whether the model can inspect files in a repository. The baselines include the base model with the full prompt, a compaction agent that summarizes when context fills, CodeAct-style coding agents that execute code but keep the prompt in context, and off-the-shelf coding agents. The key question is whether the scaffold lets the model do work proportional to the task, not merely fit the prompt into a window. The results support the design. On the quadratic pair task, the base model scores near 0, while the RLM jumps past half of the F1 score, and deeper recursion helps further. On the multi-document research task, the base model cannot even fit the input, while the RLM reaches over 90% at a cost similar to the best baseline. Performance degrades far more slowly with input length and task complexity, and the RLM handles inputs beyond the nominal context window, sometimes millions of tokens. Cost is comparable at the median, though noisy trajectories can raise the mean. The paper also post-trains an 8 billion parameter model, Qwen38b, distilling successful rollouts from a larger RLM. This teaches the root model RePL and recursion behavior, cutting syntax errors and wasteful subcalls, and it improves scores across tasks. The takeaway: effective context depends on the scaffold, not only the advertised window. The approach sits in a clear lineage. Bookscore studied book-length summarization by chunking a book, summarizing the chunks, then either merging summaries hierarchically or updating a running summary. It established that long documents need structured multi-step processing, but its workflows are fixed and every merge is lossy. DisIPL, a self-steering language model approach, lets a planner emit an inference program that follower models execute, including recursive search-style procedures, showing that models can steer their own test time computation. RLMs keep external multi-step processing and program-guided recursion, but shift the center of gravity. The entire prompt remains a first-class object in the environment. Recursion is iterative inside a persistent RePL with execution feedback, so the model can recover from mistakes, and the paper stress tests the method on aggregation and pairwise tasks where lossy summary pipelines and non-programmatic subcalls fail. Bookscore contributed decomposition. DisIPL contributed self-written recursive programs. RLMs combine both with persistent state. The paper is candid about limitations. Subcall costs can explode when the model writes wasteful loops, so the mean cost exceeds the median. Final answer tagging is brittle. Models sometimes wrap a plan instead of the answer. The scaffold depends on strong Python skill, and small or non-coding models struggle. Execution is currently slow and blocking. The small-scale training result is encouraging, but training native RLMs at scale remains open. Guardrails for arbitrary code execution are not fully solved. The punchline is that recursion and external prompt access unlock long context quality, but making that robust, efficient, and trainable is unfinished research.